In today's video, I will show you how to create a Toon post-processing filter that you can apply to your scene to get a cartoon style effect. Hello ladies and gentlemen, I hope you are doing well and having a great day. The Toon Shader we are going to create applies toon shading with Sobel-based edge detection while minimizing flickering and shimmering. It smooths out high-frequency noise in the normal map and applies distance-based fading to outlines for a more stable, high-quality rendering. I already imported the model and set the sky color to a light blue color so you don't have to watch me doing this. You can use any model you like. I use this one. To get started, we will create a new post-processing filter. Let's name it Toon Filter. Then we are going to create a new filter pass and name it Toon Pass. Okay, let's edit the shader code. We will create a uniform called shading steps, so we can adjust the number of shading steps later in the shader inspector. Shading steps defines the number of shading bands. Lower means chunkier shading. Then we will create a few constants so the behavior of the shader is easier to adjust. Line thickness controls outline thickness. Larger values produce thicker outlines. Outline threshold determines edge sensitivity, lower means more outlines and higher means fewer outlines. Normal fade start and end controls when internal edges fade with depth. And depth fade start and end controls when silhouette edges fade with depth. I figured that these values work pretty good. Here we create two small helper functions, sample normal and sample depth. Sample normal converts 0 to 1 normal data to -1 to 1 and then normalizes it. Sample depth extracts depth from the alpha channel of InNormal. The blur normal function is responsible for reducing flickering from noisy normal maps. It averages 9 surrounding normal samples to smooth high frequency variations. The function getNormalEdgeSobel detects edges using surface normals by comparing the normal at the current pixel with its neighbors. Instead of subtracting the vectors, it uses the dot product, which is more stable and reduces flickering. The Sobel operator is applied to measure changes in both horizontal GX and vertical GY directions, highlighting creases, folds, and inner details. The final edge strength is computed using the Pythagorean theorem, ensuring smooth transitions between edges. The function getDepthEdgeSobel detects silhouette edges by analyzing depth differences between neighboring pixels. If the depth changes sharply, the pixel is likely on the edge of an object. The Sobel filter calculates gradients in the X and Y directions, and the final edge strength is computed using the Pythagorean theorem. This method helps outline object boundaries and silhouettes, ensuring characters and objects stand out against the background. These lines quantize the brightness to create the characteristic toon shading bands. The next two lines gets the resolution of the normal texture in pixels and calculates the size of a single texel in UV coordinates. Since UVs range from 0 to 1, dividing 1.0 by the texture resolution gives the precise step size needed to move exactly 1 pixel when sampling neighboring texels. This is essential for edge detection, ensuring the shader correctly samples adjacent pixels regardless of the texture resolution, making it resolution independent and preventing artifacts on different screen sizes. Here we are using our blur normal function. It applies a 3x3 box blur to the normal map at the current fragment's UV coordinates, smoothing out high-frequency noise to reduce flickering in the outlines. Here we retrieve the depth value from the alpha channel of the normal texture at the current fragment's UV coordinates, which is later used for silhouette edge detection and distance-based fading. On these two lines, we use our two helper functions to calculate edge intensities using the Sobel operator for both normal-based and depth-based outlines. These two lines fade out outlines based on distance by applying a smooth transition using smooth step. This prevents harsh pop-ins or sudden outline disappearance, creating a more natural fade effect. Now we apply the fading factors to the detected edges, ensuring that outlines gradually disappear over distance. This line combines the normal-based and depth-based edge detection into a single outline intensity. Here we adjust the outline thickness by scaling the detected edge intensity. This line smoothly converts the edge intensity into an outline mask, reducing flickering and aliasing. These two lines apply the final black outline to the Toon Shaded color. Here we apply fast approximate anti-aliasing to smooth out jagged edges in the final image. This helps eliminate stair-step artifacts in the final image, making the outlines appear cleaner and more natural. These two lines blend the FXAA smoothed color with the Toon Shaded image and output the final color. Okay, let's scroll to the top and include the fxaa.glsl file so we can use the fxaa function in our code. Okay, let's recompile the shader. This is quite a bit of code this time, but we are done now with the toon shading pass. Let's create a new pass for an additional FXAA pass of the entire screen. This pass will smooth jagged edges and reduce aliasing in the final output. Don't forget to include the fxaa.glsl file here also. Okay, let's recompile the shader. Finally, we are going to add the shader to the scene. To make it look better, we have to enable the shadeless option for each material of the model. My model has several materials, so I will enable it for each of them. And this is the final result. We now have a toon shader that does cell shading and outlines. In the shader inspector under the uniforms tab, you can adjust the shading steps to your likings. Leave a like if you found this video helpful and subscribe for more videos. Thank you for watching. See you in the next video. Feels so good.